In this video, we're going to look at how to sketch hyperbolas. We'll start by looking at the general shape of the hyperbola and then how each term impacts its shape. From there, we'll look at an example of how to sketch it by hand. For those who don't know me, my name is Chris Iannazzoni. I used to work as an engineer for a defence company, and I've since left that to start a career in tutoring. I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The general form of the hyperbola is as follows. The good news is that the terms in this equation are very similar to the terms of other equations that you're more familiar with, like quadratics and cubics. Let's take a look at how each term impacts the shape of the graph. Without any transformations, the basic shape of the hyperbola looks like this. It's unique in that it has both a vertical and a horizontal asymptote. The reason for the vertical asymptote is due to a divide by zero error. If I were to sub in x equals 0 into this function, I would get 1 divided by 0, which is undefined. This makes itself present on the graph by a vertical asymptote. The horizontal asymptote exists for a different reason. It exists because as you sub in larger and larger x values, the denominator of your fraction gets larger. And whenever the denominator gets larger, your number gets closer to 0. A half is larger than a quarter, is larger than an eighth. As that denominator gets larger, it gets closer and closer to 0. Sometimes it can be hard to memorize what quadrants the hyperbola occupies. For this, I recommend subbing in a random x value. For example, if we were to sub in a positive x value, say x equals 1, we're going to get the solution y equals 1. If both x and y is positive, that means that that point exists in quadrant 1. From there, I can either remember that the hyperbola is symmetrical, and therefore the other half is going to be in quadrant 3, or I could go ahead and sub in a negative x value. For example, if I subbed in x equals negative 1, I would get y equals negative 1. When both the x and the y are negative, that means quadrant 3. The a term in the numerator is a dilation factor from the x. It's responsible for stretching the graph vertically. If a gets larger, then the curve goes further away from the axes. If a gets closer to 0, then it gets closer to the axes. The b term is very similar to a. It works in the opposite direction though. So as b gets larger, we actually see the hyperbola get closer to the axes. And as b get closer to 0, the hyperbola stretches away from the axes. Reflections are identified by a negative sign out the front of the hyperbola. The good news is that when it comes to hyperbolas, a reflection in the x is mathematically identical to a reflection in the y. So as soon as you see a negative sign on your hyperbola, you know that all you have to do is flip the quadrants. Instead of occupying quadrants 1 and 3, it's now going to occupy quadrants 2 and 4. The last thing we'll look at are the translation factors. These are responsible for shifting the graph horizontally and vertically. Horizontal translations are determined by the h term. If you have x minus h, then you're shifting your graph to the right by h. For example, if I had x minus 1, then I'm shifting my entire graph to the right by 1. When it comes to hyperbolas, you can think of this as shifting the location of your vertical asymptote. If you instead had x plus h, then that means you're shifting to the left by h. In this example here, we have x plus 2, meaning we're shifting that entire graph all the way to the left by 2. Vertical translations are determined by the c term. If you have plus c, then your graph is being shifted upwards by c. For example, if I have 1 over x plus 1, then my graph is being shifted up by 1. In the case of hyperbolas, you can think of this as shifting the location of the horizontal asymptote. If you have minus c, then the graph is going to move down. In this example here, we have 1 over x minus 2, so the graph is being shifted down by 2. So, when it comes to actually sketching these by hand, there's 3 things you need to know. The first is going to be where the asymptotes are, the second is going to be where the axes intercepts are, and the third is optional. If you have a restricted domain, you're going to have to figure out where are the endpoints. We can use the following framework to help us out when it comes to sketching these hyperbolas by hand. Let's have a look at an example. To start with, we just want to make sure that we're using the general form of the hyperbola before we begin. The reason why we do this is because it makes it much easier to figure out what each of the actual terms are. In this case, all we have to do is take the coefficient of 2 off of the x out as a common factor. From here, we can easily identify where the asymptotes are. In this case, we have a horizontal translation left by 2, meaning that our vertical asymptote is going to be x equals negative 2. Our vertical translation is responsible for giving us our horizontal asymptote, in which case we now have a horizontal asymptote of y equals negative 1. Now we move on to solving the axes intercepts. There's nothing special going on here. When it comes to solving x-intercepts, you're just going to sub y equals 0. And after a bit of rearranging and cross-multiplication, you'll see that this basically just boils down to solving a linear. For y-intercepts, you're just going to sub in x equals 0. This is much quicker to solve. The next step in the framework would be to solve the endpoints if applicable. Now, in this question in particular, we're not going to have a restricted domain, so solving the endpoints is irrelevant. So with that in mind, we have all of our key features. All we're going to do is plot them on our axes and then draw the curve connecting those points. If there is a restriction on the domain, then what we're going to do is find the endpoints of our graph. And we do that by just subbing in the x values of the lower and upper bound into the original function to get the corresponding y values. Once you have those coordinates, you're just going to cut the graph off early at those spots. Just be mindful of the bracket usage. If you have square brackets, then you should draw a full circle. If you have rounded brackets, then you should draw an open circle. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.